What if I could tell you it were possible to create a cube so wholly that it were wholly made of holes?
And what if I could tell you it was possible to make a cube so expansive that its vastness knew no bounds?
And finally, what if I could tell you that those two cubes were one and the same?
To discover this, we're going to have to travel into the world of fractals.
Carl Menger was a mathematician who discovered the Menger sponge in 1926. Among his many contributions to the field of mathematics and geometry, he's perhaps best known for his work on the Menger sponge. It was first known as Sierpinski sponge, which is a three-dimensional version of the Sierpinski carpet, another form of fractal. But you'd be surprised to learn that the Menger sponge is truly described as a simple fractal curve.
Wait a minute. What's a fractal curve? Suppose you have a square. And suppose you split this square into 4 smaller squares. Now, suppose you split each of those 4 smaller squares into 4 even smaller squares.
Now, suppose you took each of those 16 even smaller squares and split each of those into 4 teeny tiny squares.
Such a procedure can be repeated infinitely many times, meaning this square of squares has a detailed structure at arbitrarily small scales. This is what we call a fractal.
I can show you an example with a little more detail and cleanliness than the drawings we had before. On the screen right now you see a cube. You see a blue face, a green face, and a red face. We're going to take this cube and turn it into a Menger sponge. The way that we're going to do that is by taking the cube, splitting it into a 3x3x3 grid so that we think of it like a Rubik's Cube, and then removing certain cubes from that 3x3x3 grid. Let me show you the first iteration and then I'll explain more. This is the first iteration of the Menger cube. What we've done is we've split the cube we started with into a 3x3x3 grid and then removed the center cube from each face of the cube we started with and the very center of the cube itself. We can see this if we move over just a little bit. You can see that we've actually removed the very center of the cube and we can now see through it. So this is the first iteration of the Menger sponge. And just like we can have squares inside of squares inside of squares, we can have this Menger sponge inside of itself inside of itself. We can apply that same procedure of splitting a cube into a 3x3x3 grid and then removing the center cube from each face and the center cube from the entire cube itself. We can apply that on a smaller scale to each cube of the 3x3x3 grid that remains from the cube that we started with. Let me show you that. We now see that each cube from the 3x3x3 grid that we started with just a moment ago now is missing the center cube of its own 3x3x3 grid and the center cube of each face on its 3x3x3 grid. We can apply this property once more and see a level 4 Menger cube, the next iteration. Now to generate a Menger sponge, we iterate on this process infinitely many times. And you can imagine this same removal process happening over and over and over again. Now I want to pose a couple questions to you. You might notice that this first iteration of the Menger sponge looks like we see that again on a smaller scale within each of these smaller cubes. And then if we apply it again, it's like we see little copies of the first iteration of the Menger sponge. And we see lots more little copies. I wanted to point that out to you. And then another question I have for you is this. If with each iteration of the Menger sponge, we remove cubes, then if we repeat this infinitely many times, we continue to remove volume from the cube that we started with, and we expose more surface. Each time we remove cubes, we expose more surface that wasn't previously shown. So we increase surface area and decrease volume with each iteration that we apply this procedure to generate the Menger sponge. Let's see if we can unpack the math of this a little bit more and see what's going on.
Let's start with the volume. When we compute an equation for the volume of the Menger cube over each dimension change, we want to start with what we currently have for the volume. So in a 3 by 3 cube, that's going to look by 3 by 3 by 3 cube, it's going to look like 27 cubes in the whole thing. And then after an iteration of the Menger cube, where we're removing each cube, including the middle cube, as part of your 3 by 3 grid, you end up with 20 cubes after a single iteration. But as we change the dimensions n times, you realize that as n grows, your volume gets lower and lower to the point where the limit as n reaches infinity is eventually 0. But when we consider the surface area, as we iterate more and more and we create more holes in the cube, the levels of exposed surface increases. So our surface area increases eventually to infinity. So how does this work? We created a shape that has eventually no volume and infinite surface area.
A self-similar object is an object that is similar to itself at different scales. Let's take an example. Suppose you have a triangle. Now suppose we create another triangle inside of this triangle. We now have two copies of a triangle that is similar to itself at a smaller scale. This large triangle is similar to the smaller triangle inside of it, and the smaller triangle lives inside of the large triangle at a different scale. This is a self-similar object, and fractals often display self-similarity.
It's important to also know that not all fractals are self-similar, but they often are, including the fractal that we're investigating in this video, the Menger Sponge. Further, not all self-similar objects are fractals. For example, a line is self-similar to itself, but it's not a fractal. So, if not all fractals are self-similar, and not all self-similar objects are fractals, then what exactly defines a fractal? To the whiteboard.
To truly define the concept of a fractal, we need to revisit the idea of a dimension. Let's look at a couple of objects that are traditional for thinking about 1D, 2D, and 3D. We've got a one-dimensional line, a two-dimensional square, and a three-dimensional cube. Now let's consider splitting each of these shapes into smaller copies of itself. What we're going to do is scale each of these shapes, their lengths, by a factor of 1/2. If we scale down a line by a factor of 1/2, we can fit two smaller copies of the line into the original. If we scale down a square by 1/2, we can fit 4 smaller copies of the original square inside the original square. And lastly, if we scale down a cube with a side length of 1/2, or with a scale factor of 1/2 on its side length, then we can fit 8 smaller cubes inside of the original cube. Let's look at this in a little more detail. For the one-dimensional line of length 1, when we scale the length by a factor of 1/2, the size of the lines that we get, these smaller lines, is also 1/2, which is 1/2 to the first power. For the two-dimensional square, if we start with the square of side length 1, and then we scale the side lengths by a factor of 1/2, the resulting smaller square has a size of 1/4. That's 1/2 to the second power. Lastly, for a three-dimensional cube, if we start with the cube of side length 1, and then we scale the side length by a factor of 1/2, we get a smaller cube that has a size of 1/8. That's 1/2 cubed. Here, in the exponents of the factor that we use to scale the side length, we see the dimension of the shape appear. So how do we generalize this to an n-dimensional shape? What is the idea of a dimension? Well, a shape in n dimensions can be compared to a scaled copy of itself. We can take an original shape in n dimensions that has a length of L and a size of M. Then we can look at the scaled copy using a scale factor S. Previously for us that was 1/2. A scaled copy of a shape in n dimensions, scaled by a factor of S, will have a length of S times L and a size of S to the power of n times n. This n is the dimension of the shape that we live in. For those of you interested in learning more about the math and the details behind this, I highly recommend 3 Blue 1 Brown's video on the topic. Let's see if we can apply this a little bit to a square and then a Menger sponge. Consider 2 squares, an original square of side length L and size M, and then a scaled, smaller square using a scale factor of 1/2. The length of this smaller scaled square is going to be s times L, 1/2 of our original length. The size, because squares are two-dimensional, is s to the power of 2 times m, or 1/4 times m. Let's contrast this with the Menger sponge and see if we can learn anything. Consider a Menger sponge, or a cube, that has length L, side length L, and size m. And consider a smaller portion of the Menger sponge. Consider applying one iteration of the cube deletion process that we discussed earlier. The side length of one of these cubes is now going to be s times L, where s is 1/3. It's going to be 1/3 times L. And that's because with each iteration, we split the sponge into a 3x3x3 grid. Now, what's the size of this? Well, we know that the size is going to be 1/3, our scale factor, to the power of the dimension times the size of the original cube. Let's see if we can solve and figure out what dimension a Menger sponge lives in. The size of the smaller scaled cube is the mass that we started with divided by 20, because we remove 7 cubes out of 27 cubes from our 3x3x3 grid at each iteration. So the mass that we started with divided by 20 is equal to 1/3 times the power of the dimension that we live in times the mass that we started with. That is, the size of the Menger cube is equal to the size determined by the iterative deletion process. Now we can solve with some logarithms in algebra and find out that the Menger sponge lives in 2.72 dimensions. What does that mean? And what is a fractal? Well, one way that we can think of a fractal is it is an object that has a dimension that is non-integer. So a line has 1 dimension, a square has 2 dimensions. The Menger sponge has 2.72 dimensions. 2.72 is not an integer, so the Menger sponge is a fractal. And a cube has 3 dimensions. There are some details here. Not all fractals truly have non-integer dimensions. It's a good generalization and a good idea. It gives us a good sense for something that can be used to better define a fractal than self-similarity.
Fractals are much more than just mathematical curiosity. They appear in nature and in our real world in things like geography, and they merge simplicity and complexity in fascinating ways. You can see this in our Menger Sponge program that we created. As the levels increase, you can watch yourself as the self-simplicity increases in depth and volume goes to 0 as surface area increases. Thanks for joining me on this journey through the infinity of fractals. I hope this video sparked your curiosity a little bit and reminded you that mathematics isn't just about solving problems, but reflecting the real world, discovering beauty, and finding patterns where we least expect them, seeing the extraordinary in the ordinary. Stay curious.